Do you remember when we did the limit definition of the derivative, and it was a lot of work, and then I showed you a shortcut?
Yeah.
Okay, do you remember how satisfying that was? Okay.
What was it?
Because we had to do all of them.
Okay. Today is sort of the same thing. Okay. We've done a lot of work with those Riemann sums. And then I showed you that you could use geometry, right? Well, if you had to do a Riemann sum every time that you needed to do a definite integral, you would lose your mind. Okay? It's a lot of work. It is. But the concept of what we're doing to get there is important, which is why we do it. It's a stepping stone to get to today, the fundamental theorem of calculus. Okay? I'm emphasizing fun because it is. All right? It all comes together today. Today is like the finale of we did these antiderivatives, and then we did this weird area stuff, and then we kind of mixed the two together, but we really haven't come back to taking antiderivatives. That's where it comes together today. All right? So our fundamental theorem of calculus is this. Go ahead and write this down. If a function is continuous on a to b, and f is an antiderivative of f on a to b, just write it down so you know the background of it. So we need a continuous function, and we have a relationship between a function and an antiderivative. A little less big F. Oh, because I said I know what you're Okay. The integral from a to b of f of x dx. First of all, let's talk about what this means. What are we calculating when we take the integral from a to b of f of x? What are we calculating? The area under the curve from a to b, right? Now, when we talked on Wednesday, we took infinite limiting rectangles and added them together. That's what we were doing with the Riemann sums. Okay? Now, shortcut. What we can do is we can take the antiderivative of b minus the antiderivative of a, and we're done. Celine's smiling. She knew this was coming. So she didn't have any of the trig background that you have, and so anything that we do trig, she hasn't really seen before. So she is learning, but she has like some of the foundations.
So Germany is better education.
Germany teaches math differently. Last year, she learned calculus and stats and pre-calc and like all at one time. So they have more of like the like an integrated approach where you're learning like all types of math in 1 year, as opposed to where we like chunk it out. Does that make sense? Okay. All right. Now, I in the past have gone through a very formal proof as to why this is, but I don't know how much like ownership you really take from it, like how much you really get away. So I'm gonna try to explain this to you in something that you can relate to a little bit better. Okay? A lot of you have had physics, and so I think that this will resonate with you a little bit better. So let's imagine we have a velocity time graph. And you don't need to write this down. I just want you to play along with me, okay? We have a velocity time graph, and let's take a chunk from A to B and calculate the area under the curve. Okay? Well, what are we finding? Okay? If we're taking these rectangles, this area under the curve, okay, our height is velocity, our widths are time. What do we get when we take velocity times time? We get a distance. I'm going to call it position. Is that okay? Position. Okay. So when we're finding the area underneath a velocity curve, we're finding a distance that is traveled, or maybe the position in which that particle is in. Okay? So now, let's think about this. If I were to start right here at point A and walk right here to point B, how would you find that distance? Let me reword that. Here I am at x equal, here I am 5 feet away from the wall at point A, and now I am 15 feet away from the wall at point B. How do you find the distance that I've traveled? Okay, so what you're saying is to find my distance, I could take the position that I have at B and subtract the position that I have at A. S is position in calculus, just get over it right now, okay? Okay. Well, we just decided, I'm going to come back to here. Okay. We just decided that velocity times time was distance. So this right here that we did was the integral from A to B of our velocity. Can anybody tell me what the relationship is from velocity to position? Physics people? Okay, let's use some calculus words. It's not always, well, it's not always, like, what do you mean by linear? Let's go back to it. What do you mean by linear?
Like the function,
Okay, so that's not always the case. Like, our position's not always going to be a linear function. Like, if we have, how about I ask you this? If we have so what you're thinking of like a falling object, and how if we had acceleration, it was quadratic. If we had velocity, it was linear. And then we had position. Is that what you're thinking of? Like back first semester, when we had like the 1/2 gravity times time squared stuff.
Yeah.
Like, is that what you're referring to with the linear? No. Okay. Well, I'm trying to get where you're going, because we're gonna look at position curves that aren't necessarily linear. Okay, they don't have to be linear. That's what I was trying to get out of that. But think about the relationship from calculus. Go back to what we did first semester. Our falling object, we had our velocity was gravity times times squared. Remember that falling object stuff that we did, like the 1/2 gravity times squared, yada, yada, yada. Okay? What was the relationship from our velocity equation to the position equation? Okay, so let's use a calculus word. What was the relationship from velocity to position? It was the
Derivative.
oh, okay, because of the 1 degree left, right?
10 minutes ago.
You gotta say it louder, Braden.
Use the big boy voice.
It's the derivative.
Thank you. So, Braden, what's the relationship from position to velocity? There we go. Antiderivative of v minus antiderivative of a. Okay. Now,
So can we go over that?
what'd you say?
Just gonna go over that one.
What is something missing up here from when we took antiderivatives before? What? I didn't write the plus C. What does that make you say? We don't need it. The point was we don't need it.
Oh.
Thinking I forgot something. Okay. So we did our stepping stone of the Riemann sum, so you understood what was happening, how we were finding the area. But now the integral is that summation. You will have to do a Riemann sum on a quiz and a test, but then that's it, okay? We can now just work on our fundamental theorem of calculus. Now, let's talk about why we don't need that plus C, okay? So let's just say that we have the integral, and this is something you can still just watch me do, okay? If we have the integral from a to b of f of x dx, then we know that its antiderivative is capital F plus c. And then we would have to evaluate it from a to b. Well, if we use the fundamental theorem of calculus, we plug in b for our antiderivative, and then we subtract, plug in a. Brem, what happens? The c's cancel out, so we don't need them. If we have a definite integral, meaning we have these numbers right here, if we have a definite integral, we don't need the plus c. All right? All right. Let's do some work. Please write down the integral from 0 to 1 of 3x squared plus 2 dx. I have a picture for you over here. Here is our curve. From 0 to 1, we are finding the area underneath the curve. Geometry is not going to help us with that. That's fine. We don't need to do a Riemann sum. It's fairly tedious. Okay. What we can do is we can take the antiderivative and evaluate it from 0 to 1. So, the antiderivative of 3x squared plus the antiderivative of 2. And then you're going to make this vertical bar, that means evaluate, and you're going to take your limits of integration, and you're going to place them there. These are called limits of integration. You want to plug in b first, and then subtract plug in a. So, when we plug in 1, we get 1 cubed plus 2 times 1 minus, plug in A, 0 cubed plus 2 times 0. What do we get? Take your calculator, math 9, plug this in, make sure we got it correct. Anybody else have a CI 83? Does anybody not get the integral symbol when they plug in math 9? Did you get it right?
Oh, I sent it
Yay! Okay, now I showed you math 9 so you can check your work, but I better see some work. Okay. Otherwise, I'm gonna assume that you have used your calculator. All right. That's the big idea. That's all we're doing. Okay. Can you handle it? Can you handle it? Okay. Write this one down. You don't? What will you do? You gotta be brown. Okay, so don't forget all of the work that we did. How long has it been? 2 weeks ago, right? I don't even know. With our antiderivatives, okay? I would rewrite this to be 3x to the 1/2 before taking the antiderivative. Okay? Matt, what is the antiderivative?
2x to 3x.
Like that?
Yeah.
Okay? I'm gonna, just in case, this is 3 times, since this is 3/2, we say 2/3, and so those 3's canceled, which is how we got the 2 as a coefficient. All right? And we are evaluating from 1 to 4. So we have 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. Without your calculators, what is 4 to the 3/2? 8. The square root of 4 cubed. 8. Okay. So we have 2 times 8 minus 2 times 1 to the 3/2 is 1. $14. You said it was math 9? All right. All right. So much better, is that what I heard? It really is.
Yeah.
We're having so much fun.
It's too much fun? It is a fundamental theorem of calculus.
Well, I wouldn't call it fun.
No, it is fun. It is get rid of all that.
Is it more fun to do this or Riemann sums? Okay. Our definitions of fun may be different, but we can all agree that this is better than a Riemann sum. All right. Now, keep in mind our rule quizzes will continue to happen this chapter. You lucked out today. I didn't have one for you. Okay.
So Monday.
I don't know. I don't know when I'm going to do it. Ethan, what is the antiderivative for secant squared? Tangent. So the tangent of x from 0 to pi over 4. Using the fundamental theorem of calculus, we have the tangent of pi over 4 minus the tangent of 0. What is the tangent of pi over 4? 1. Remember, that's the coordinate radical 2 over 2, comma radical 2 over 2. So y divided by x is going to be 1. What is the tangent at 0?
0.
Okay. When you use Math 9 and you have a trig function, you better be in radian mode. Okay. So check your calculator, make sure you're in radian mode, and then try the Math 9 command to calculate this antiderivative. Remember to enter in secant, you must do 1 over cosine, because those are reciprocal functions. So 1 over cosine squared. Well, what I was going to say is have x inside, but then you open up that one. So close the cosine, close the denominator. Oh, that's nice. Yeah, that's nice. Because you still have that vertical line. Yeah, that would be just fine. Yep. Somebody in Wisconsin Titan time. I don't know. I come in here and he draws on my board, and I wasn't here yesterday, but isn't it? I know. I feel bad when I have to erase them, but could I use that? I used it yesterday because I had a sub and I left some notes. So he had drawn one Wednesday that I had to erase so I could draw that up. But I know I'm not that artistic. Okay, we have 2. We have 2 more problems. Each of these will take maybe a minute. Well, this one will take less than a minute to do, but then we'll talk about it. Oh, man.
I was going to say.
There we go.
There's going to be a big twist.
Oh, I've never seen this before.
I wasn't ready for it.
Okay. Oh, and what's the antiderivative to cosine?
Sine.
I'm hearing whispers of, is it negative, is it positive? Okay, because the derivative of sine is cosine. So we have the sine of pi minus the sine of 0. What is the sine of pi? What is the sine of 0? Does that seem right?
Yep.
Ooh, that was actually pretty good. Okay, here's our cosine curve. Here's pi right here. Does it make sense that the area from 0 to pi is 0? We have 2 symmetric pieces right there, so we know that they're going to cancel each other out. Okay? We didn't even really need to do calculus for that. We could think about the picture, right? All right. Last problem, then we're done.
No, I do.
Oh, okay.
I see somebody from class like, I don't know what's going on, but I said, can you go to the
All right, what do we got to do with this radical x? Bring it up and actually put it to both, okay? We can only use the power rule. So this is from 1 to 4 of x to the 1/2 minus 2x to the negative 1/2. And now we can take the antiderivative. Don't forget about all of those rules that we practiced in the beginning of the semester. Okay? So now we have x to the 3/2 times 2/3 minus 2x to the 1/2 times 2/1. Evaluated for 1 to 4. So we have 2/3, 4 to the 3/2, minus 4 times 4 to the 1/2. There's f of b minus f of a. Okay. What's 4 to the 3/2? Times 2/3 is 16/3. Minus 4 times 4 to the 1/2 would give us 8. Minus 2/3 minus 4. Okay, so I'm going to do this. What's 16/3 minus 2/3? 14/3. Negative 8 minus negative 4. So now we have 14/3 minus 4. Can you be positive? Okay, so I know that we're like super off on our gold sheets. Our homework assignment is the first fundamental theorem assignment. So page 288 on 128. Like it's supposed to be January 28th, but I'm giving it to you today. So this is all about the first fundamental theorem. On Monday, what we'll do is we'll come back to our U substitution and how that affects the first fundamental theorem of calculus. All right? Okay, have a wonderful weekend.